In this session, we're going to talk about the Nernst equation, which is another way of saying we're going to talk about the relationship between electrochemistry and equilibrium. You can read about this in sections 17.3 and 17.4 in your textbook. And in particular in this session, we're going to talk about calculating with the Nernst equation, and we'll talk more about electrochemistry and equilibrium in the next video. So we've looked at this cell several times before, and we have worked out that the balanced chemical reaction for this electrochemical cell is that copper metal reacts with silver ions to produce copper ions, copper 2+, and silver metal. And using standard reduction potentials, previously we worked out that the standard cell potential is positive 0.46 volts. So this is a galvanic cell. It is spontaneous in the forward direction, the way we've written the reaction. Okay, so keeping that in mind, imagine you have this cell and you added additional silver ions to the cathode compartment. So we add more silver to this side. What would we expect the reaction to be more or less spontaneous in the forward direction? So this should make the reaction more spontaneous in the forward direction because, as we said before, the silver ions are a reactant. So we're adding a reactant. Okay, which means we're going to have we're even further away from equilibrium. So we have even more potential energy to proceed toward equilibrium. You can also think about this, start to see the connection to Le Chatelier's principle here. If we have more reactants, then the reaction, even more, wants to go to make products. Okay, so if the reaction is more spontaneous in the forward direction, how would we expect the cell potential to change compared to the standard potential? Now remember, the standard potential is calculated when we have 1 molar of each of the aqueous solutions. So if we added more silver plus, how's that going to change the potential? So since the reaction is going to be more spontaneous in the forward direction, that means that the potential of the cell under non-standard conditions is going to be more positive than the potential of the cell under standard conditions. So the standard conditions represents 1 molar of each. If we add more of the silver ions, we're now under non-standard conditions. But since we're more spontaneous, then that means that the potential would be more positive. We can represent that mathematical relationship with the Nernst equation. So the Nernst equation is named for Walter Nernst, who was a chemist in the early 20th century. He's a contemporary of people like Boltzmann, or usually actually a student of Boltzmann, contemporary with Arrhenius. So he was actually an advisor to Lewis of Lewis structures. So he's one of the dudes. And we see that, so the Nernst equation tells us how the potential of a cell under non-standard conditions is affected by the conditions. So things like the concentrations, Q. So this Q here is the same Q that we've dealt with before. We can also see that this is going to show us how the potential will be affected by temperature, because under standard conditions, the temperature is 25 degrees C. Now, so R here is the ideal gas constant. F is Faraday's constant. Okay, and this is the relationship between coulombs, or charge, and moles of electrons. Coulombs per mole of electron. And N is the number of electrons that are transferred in the reaction. So we have to think about, how many electrons sort of get canceled out when we balance the reaction. Okay, so because R and F are constants, we can, so here we have natural log of Q. So the first thing we can do is convert use this 2.303 to convert the natural log to base 10 log. And then since R and F are constants, and because most of our chemistry, we're often doing at room temperature at 25 degrees C, we can combine all of that, really all of this, combine all of that, and we find out that it is 0.0592 volts. So we can simplify this equation where this is the potential of a cell under non-standard conditions equals the standard cell potential minus 0.0592 volts divided by the number of electrons transferred times log of Q, where Q is that ratio of products to reactants. So when should you use the different forms? I think that for the most part, the most useful one we'll find in this class is this last one, where we've had all the constants simplified. If you want, you can go all the way back to the beginning. You'll just find that it's kind of repetitive. Okay, so let's see how that works. Here's our cell again. Let's calculate the cell potential, E, without the little degree sign, when the copper concentration is 0.1 molar and the silver concentration is 0.5 molar. All right, so we need the Nernst equation. We need the Nernst equation. E equals E naught minus 0.0592 volts divided by N times log of Q. And so we're trying to find cell potential E, so let's start filling in the things that we know. We know that the standard potential is 0.46 volts. And then the, if we got 0.492, the number of electrons transferred. So this needs to be the total number of electrons transferred. And in our balanced chemical reaction, we see that we need 2 equivalents of silver for every 1 equivalent of copper. So that means that the total number of electrons transferred is going to be 2 if you were to work out how many electrons you would have in the balanced half reactions. And then log of Q. So Q is going to be the concentration of the product, so copper, divided by the concentration of the reactants, so silver squared. Now, why aren't the silver metal and the copper metal in the Q expression? Because they're solids. They don't go in the equilibrium constant expression. And then remember, we need the squared because in the balanced chemical reaction, the coefficient on silver is 2+. So we can put that into our reaction where the copper ions are 0.1 molar and the silver ions are 0.5 molar squared. Okay, so when I do that, I get 0.46 volts minus, and then this whole term comes out to be negative 0.012 volts. Okay, so when I put all that together, I find that to 2 significant figures, I get 0.47 volts. So what we see here is that adding more silver relative to the copper makes our potential slightly higher, slightly more positive, but it's not a big difference. Okay, so changing the concentrations changes the potential, but it doesn't change it a whole lot. Okay, so let's think about this again. For this cell, the standard potential is 1.1 volts. Okay, under standard conditions. Now, if you measured a particular one that you made and it was only 0.21 volts, what would that tell us about the concentration? Is the zinc concentration higher or the copper concentration higher? Okay, let's think about how we would think about that. So this cell potential, 1.1 volts, that is the standard potential. The 0.21 volts is the standard potential under non-standard conditions. If we think about the zinc and the copper, if we look at the direction that things are going, so then that means that this is the anode and this is the cathode. So in this cell, the zinc solid and the copper ions are both reactants, and they're producing zinc ions and copper metal. Okay. And so here the observed potential is much smaller than the standard potential under non-standard conditions. So we have less potential energy, or put another way, this reaction is less spontaneous in the forward direction. And so what that might mean is that we have a lot more products than we have reactants. And so if we have more products than we have more reactants, that means we're going to have more zinc ions than we have copper ions compared to standard conditions. Okay. Now, when would you ever use this? So you can also measure the potential and compare it to standard conditions and use that to calculate concentration. This is how things like pH electrodes work. Also, blood glucose meters are using electrochemical reactions. And some AlkaSensor is a type of breath alcohol analyzer that uses electrochemistry. The breathalyzer brand actually uses a different reaction. But so here's examples of how you could use the Nernst equation, the difference between standard conditions and non-standard conditions, in order to find out something useful. Okay, so this has been the Nernst equation. In the next video, we'll talk more about the relationship between potential and equilibrium.